last week we looked at the general operation of your power system from a management standpoint. On our operational standpoint, we spoke about, well, we briefly mentioned economic dispatch. We looked at scheduling of generation, yes, or commitment, generation commitment, where we consider the technology used and the cost of that technology, the availability of the technology in order to dispatch units accordingly. Today, we're going to spend some time looking at economic dispatch, where we look more at the operation of the generating unit in determining the dispatch and how these units will go about taking on load. Now, in saying that, let me just segue a minute from today's lecture and speak briefly on lab number 2, which I have started marking, because I know that in that set of reports, you have been making some statements that suggests that there isn't much clarity in terms of really how a power system operates. Yeah. So a couple of things. The lab specifically spoke about load angle at the bus bars. Yes. But persons were making heavy weather, so to speak, of power factor. Also, in terms of correcting the voltage at the bus bar, persons were focusing primarily on power factor correction. Now, power factor correction is something completely different. Whilst we may use the same technology per se in terms of achieving both, power factor correction is about a load or at a facility where you're trying to improve I shouldn't even say improve, but you're trying to reduce the amount of reactive power being consumed in supplying the same active power. Now, I saw persons use words as efficiency and power factor is the level of efficiency of using power. That may have been stated in some piece of literature, but from a power system standpoint, that's not really what we are considering when we are looking at reducing reactive power. What we are interested in, students, is the fact that for a customer who is charged for the reactive power that they consume, these customers are charged based on the apparent power. So the utility company charges based on volt amperes or apparent power. Now we know that the apparent power, if you go back to your power triangle, the apparent power is on the hypotenuse. The active power is what the customer utilizes. So the active power is what is actually consumed in carrying out whatever operation they are carrying out. However, that active power, depending on the equipment at the customer's premises, that active power will, that active power being consumed will come with a certain reactive power requirement. So you have the active power, which doesn't change because the equipment at the facility requires this power. But then you have the reactive component. Power factor correction is what you do in reducing the magnitude of the reactive power in order to lessen or reduce the magnitude of the apparent power for which the customer will be charged. Do you understand that? Is there, does that make it any clearer for you?
Yes, sir.
Yes, sir.
All right. So when we're talking about from a power system operation standpoint now, our objective in using reactive power is to impact the voltage at the bus bar. All right. So it's the voltage at the bus bar that we're trying to impact. Um, the other thing I want to point out, there, I mean, sometimes we use words and for the most part, we can understand them, but in a certain context, especially in the engineering context, we have to be careful how we use certain words. There is a distinction between quantities having an inverse relationship and them being inversely proportional. There's a big difference. All right. Of course, and also um, it's important that we be clear in our minds when we use the term directly proportional. Because the word proportional has a specific meaning. If something is directly proportional, what it means is that there is a set relationship in terms of increases on both sides. So if one increases by a certain amount, the other will increase by a certain factor. And that direct proportional, keyword, proportional relationship would be maintained. And as such, for direct proportionality, you would have a straight line. We all know that. On the reverse side, whilst you may not end up with a straight line, yes, direct inverse proportional speaks to reduction in one component, giving a similar reduction in the other. So you have proportional inverse relationship. Okay? However, when you have an inverse relationship, it doesn't mean that if one is reduced or increased in one way, the other one will be increased in a decreased in a specific way. All it is saying is that as one increases, the other decreases. But the increase and the decrease, or the decrease and the decrease, are not proportional. And I see several persons using that term in describing the relationship between uh, uh, reactive power and, say, voltage level at the bus. All right? Now, I go further with this because the other error, major error that I see persons making, which I'm a little disappointed in, because what we are being trained for, students, is to be engineers. Huh? And one of the responsibility of an engineer is to, you have an objective, because all your life, you're going to be doing labs. You may not realize it, but that's what you'll be doing in engineering. You'll have objectives. You have an aim, and you have certain objectives for that aim. You're going to be making a determination as to how you are going to address these objectives. That is where your theory comes in. Of course, we have already discussed the fact that I give you the method, so you don't have to worry about that. But let's now come to the whole business of discussion and coming to a conclusion. When I asked you to hold, for example, or to keep the active power fixed and to vary the reactive power, what will happen is that there will be changes in both the load angle and the voltage levels. Fair enough? So if you keep P fixed and vary Q, you're going to see changes in both. However, as someone who is looking, or the objective, listen, the objective is to determine the impact on load angle and voltage level. Yes, that's your objective with respect to P and Q, right? That's the objective. P fixed, Q varies. Delta and V will both change. However, the change in V is going to be more significant than the change in delta. When you do the reverse in holding Q and varying P, you're going to see a greater change in P in delta rather than V. So at the end of your lab, and I was shocked, but at the same time quite disappointed, because at the end of your lab, you're asked to make conclusions, and people are afraid to make decisions. And I have said before, the conclusion you arrive at, even if your results is pointing you in a different direction, you have to conclude based on the results. So, given those changes that I just mentioned, at the end, you don't need to go back to your objectives and say, all right, what are the impacts of P and Q on V and delta? And so the concluding statement must be, one, the load angle is impacted more readily by changes in the active power at the bus bar. That's conclusion number one. Conclusion number two, the bus voltage is more impacted by changes in the reactive power at the bus bar. Those are your two concluding statements. End of discussion. Because your objective was, what is the impact of P on delta and V? What's the impact on Q on delta and V? Right. So I'm not going to, for use of a better word, go easy on you. It is important, very, very important, that you make these decisions, because that's what we are training you for, right? To make decisions. And having made those decisions, yes, well, I shouldn't say having made those decisions, but you are going to be looking at the data before you make those decisions, because as I have said, hopefully in this class, yes, your purpose as an engineer is to save your company money, while not only saving them money, while helping them to make money by improving processes. That's your purpose. If you are not able to save your company's money, your purpose as an engineer would be lost, and they will have no need for your services. Do you have any questions based on what I just went through? There's a little more that I will say when I review your labs, and when you do the oral assessment. But I think it is important that we get that clear in our minds before we go any further. So, do you have any questions or comments? No? So I expect therefore to not see any equivocation um, on the conclusions for lab 3, and we have already submitted it, but I hope I'll be able to see more precise language from you as students. All right, so today we want to look at the dispatch of generation based on economic operation. All right, and we're going to be looking at what we refer to generally as economic dispatch. Okay, so what we have before us here is the operating cost in dollars per hour of a fossil fuel generating plant. And this is plotted against the power output in megawatts. All right. So we have the operating cost in dollars per hour. And note that the axis can also be given in BTU per hour. Because technically speaking, given that this is a thermal plant, yes, you're looking at really heat production, yes, and in terms of the amount of BTU that you are producing, BTU, British Thermal Units, in terms of the amount of BTU that you are producing, it really amounts to you burning money. So whether you are using oil or natural gas, yes, in terms of the amount of BTU that you are producing, it is equivalent. Because as you produce this BTU, you'll be consuming, so much cubic feet of gas or so many barrels of oil, you name it, right? Or gallons of diesel, you name it. It's really about heat production. So the comparison, and by the way, you'll have these figures already in Schoology. So, just get access to them so we can, as I go through, we can just quickly refer to them. All right. So we have it here in dollars per hour or British Thermal Units per hour. And this is plotted against the output in megawatts. Okay. Note here also that what we refer to is a generating plant. And I want to make the distinction between a plant, yes, versus a unit. All right, so let's start with that quickly. So a plant is a facility consisting of generating units. So each generator would be considered a unit, and the generators combined in that facility would be a plant. So for those from Jamaica, the B6 is a generating unit. But that B6 generating unit is a part of the Hunts Bay plant. All right? So we make that distinction. So what we are talking about here is the overall plant. Yes, and we are saying that we are looking at the cost versus the output. All right. Now, the figure that you see here, obviously it is not a straight line. And if you look on the sections, the individual sections, maybe initially they may have seemed straight, but there are slight curves in them. All right. But for the most part, each of those subsections, in some instances, can almost be considered as linear. So what we have before us here, in terms of the output curve, and yeah, I know I'm using the term curve, but yes, the output curve here is known as a piecewise continuous curve. All right, so in sections, it is almost linear. All right, then we have the jumps. Then it takes another linear path, jump, takes another linear path. So what that is saying is that there is no quote unquote direct or constant increase in terms of the BTU that is required to produce the additional output. So between 200 and 400, yes, megawatts, we are moving from just about 2 times 10 to the 9 BTU per hour up to about 350, yes. But then when we seek to go to 600, we are somewhere in the region of about 5.5 times 10 to the 9 BTU per hour. So important here, the operation in terms of dollars per hour, as I said, also in BTU per hour, but for our purposes, we're going to be focusing more on the cost, so we'll be looking on the dollars per hour. All right. Now, if we look at the incremental cost, an incremental cost, I know some of you have done or are doing econ, so this should be nothing new to you. So the incremental operating cost, and by incremental cost, what we mean is the cost of producing an additional unit, right? So the incremental cost, yes, which is the differential of the cost function, just like your econ, the econ rather, the differential of your cost function is shown. And what you will note is that at 600 megawatts, yes, the cost or the incremental cost is about $9,000 per kilowatt or 9,000 BTU per kilowatt hour. Yes, and we'll talk about that in a little more detail a few minutes. But we know that this is at the turning point. Yes. So at that turning point, of course, we know that is telling us that our unit would be operating at its highest level of efficiency at that turning point. Right? So that's the lowest point on our curve, telling us that at that point, the unit will be at its most efficient. Okay? Now, let's just, for the benefit of those who are unfamiliar with the term incremental cost, let's just talk a little about that, because I want us to be clear in our understanding about this, as it will help us in our calculations. So we have the definition here. Incremental cost being the cost of producing one additional unit, one additional megawatt. What's the implication of that? If I'm looking at operation based on incremental cost, forget that I'm talking about power systems here now. If I'm looking at operations, I'm in a factory, in a manufacturing facility, what's the importance of incremental cost? Anybody?
Not to reduce the.
Go ahead, I'm listening. Somebody was saying something about reduce, and then the person got cut off.
Sir?
Is it my internet? People are coming in and yeah, go ahead.
Would it refer to the startup and shutdown cost that we discussed last week?
No, not really. No. I'm asking, what's the implication, what's the importance of incremental cost? And I'm asking this now from a manufacturing standpoint. Is my assumption regarding persons in the class doing or having done economics, is that assumption a correct one? Is there anybody here who has not done econ or not doing econ? That was a question. Eh? Mr. Finley, where you? I can't hear you. Is it me? Mr. Finley? All right. Anybody else? I'm not hearing Mr. Finley. I see that his mic is open, but I'm not hearing him.
Sir, is it like expenses that will come during production process?
It is the cost of production, but what I'm asking, what's the importance of it as part of the production process? When I say the incremental cost, what does that mean really? Give me in practical sense. What does it mean?
Sir, I believe basically it would be like the cost as you increase in, I don't want to use the word increment again, but I believe it's a cost as you increase in the amount of output. Like it's the per unit, not per unit.
Yeah, man, you can use per unit. That would be correct.
Okay,
It's a per unit cost.
Yes, sir. As you increase in the amount of output. Yes.
So what would be the importance of that incremental cost if I am trying to reduce the cost while maximizing production? What would be the importance? Come, Mr. Bed. You're on a roll. Keep rolling.
Sir, I believe by knowing how much it would increase by, sir. Sir, I think I need some time to structure the explanation.
Fair enough. Okay. In the interest of time. Oh, Mr. Gibson, yes, you're saying.
No, sir, I was wondering if the aim would have just been to reduce the incremental cost.
I'm not hearing clearly. I don't know. Maybe if it's my internet or what.
Sorry, sir. It could be my connection. It was just that if the aim would to be to reduce the per unit or the incremental cost if you want to have a more efficient system.
All right, fair enough. The one objective is to reduce the incremental cost, but the incremental cost is that cost of producing one additional unit. Now, in a manufacturing facility, yes, and I used this example in last year, and it seemed to work. So I'm gonna try it again this year, right? Let us say I am producing bullets, all right? So I'm producing bullets. And in this factory, I have 3 production lines that's producing bullets. On line 1, the cost of producing an additional bullet is 10 cents. On line 2, the cost of producing an additional bullet is 8 cents. On line 3, the cost of producing an additional bullet is 5 cents. Right? What we would have had are incremental costs on line 1 being 10, line 2, 8, and line 3, 5. So if the cost of producing the additional bullet on line 3 is at 5 cents, as a factory manager, in order to reduce the overall cost of production, I will take additional bullets from line number 3. So I'll increase production significantly on that line until, because as I increase production, the cost may go up. Yes? So I will continue to increase output on line 3 until its cost of producing an additional bulla gets to 8 cents. When it gets to 8 cents, then I'll take bullas from both lines 1 and 2, lines 2 and 3, sorry. And I will increase production on those 2 until they get to 10 cents. And then I'll take it from all 3. But the idea here is that within the manufacturing space, the system that is producing the additional unit of product, yes, at the lowest cost will be the facility or the line which I will increase production from. Does that make it any clearer?
Yes, sir.
Everybody still lost?
Yes, sir.
Yes, sir. We get to yes, it to an extent.
To an extent, fair enough. The same is applicable to a power system. So what we are going to be looking at is what is the incremental cost for each unit within the plant. And we had already made a distinction between unit and plant. So we are going to increase output on the most efficient unit. That's basically what we're saying. Until its efficiency is as efficient as the next unit. And then we continue to do that increase. But there comes a point, as I just said, for this plant, right, we are seeing that the greatest efficiency occurs when we are at that point. So that's for the plant. We're not talking about individual units now. All right. So let's drill down and see where we go from here. All right. And as I want students with this topic, there's no straight maths for it. You have to think about this particular topic and treat with it from an economic and an engineering standpoint. All right. All right. So we have the incremental cost versus output. And so for your cost function, that consists of only fuel costs, because fuel is the primary driver. The cost derivative, dCdP, is the ratio of the incremental fuel energy input to the incremental energy output. All right? And this ratio is known as the incremental heat rate. And then the reciprocal of the heat rate is the efficiency of the generating unit. All right? So let me throw some things at you that is really practical, that you are going to hear on the radio. And as persons in the engineering space, you need to understand it. Now, in Jamaica, we operate on what is known as merit order dispatch. There's some incremental, there's some economic dispatch, but for the most part, it's merit order dispatch. And merit order is just in terms of both production costs, and there are certain criteria that are set, which will determine whether or not persons are able to connect to the network. Now, one of the things you will hear from the OUR is that JPSCO, and we know that JPSCO, there's quite a bit of I don't want to use the word flexibility because that does not give a true picture of what happens. But there is some amount of leniency, flexibility, call it what you will, in terms of the charges. So they are able to recoup costs on energy. So you will see there's an energy charge and there's a fuel charge on your bill. I know most of you don't pay like this, so maybe you won't even see this. But there's that charge on your electricity bill, your energy charge and your fuel charge. Now on the fuel, you'll see fuel and IPP. Now it is true that whatever the cost of production of providing the energy, that us as customers will have to pay for it. But to balance that out, the OUR will require of the utility and producers that they operate at a certain heat rate. So the efficiency with which they convert that BTU into electrical power is now important. So the regulator will specify the sort of heat rate that generation must be taking place. And so it forces the utility to look at the efficiency of their generating plants, their generating units in producing the energy. All right? And so what we're highlighting here is that, of course, if you have a lower heat rate in terms of operation, then the efficiency of the generating unit will be increased. Now, I know you have said that most of you have not done heats or mechanical technology, but nonetheless, if we were to convert convert that heat rate in BTU per kilowatt hour into kilowatts, yes. All right. So in terms of the conversion, we have said that this occurred. Now I know you did not see the 54. All right. That's what we're talking about. So at 600, all right, we just know that it is, based on our estimates here, we know that it is less than 6, but of course it's greater than 5. All right? I am now telling you that it is 54. All right? Or 5.4. So 5.4 times 10 to the 9. All right? So the heat rate is 9,000 BTU per hour, per kilowatt hour. And if we now convert that what else? If we now convert this, yes, the conversion factor of 3413, what we get is an efficiency of 37.92. Now, on the surface, that seems very low, but just take it from me that this is an extremely good level of efficiency for a thermal plant. All right. Yeah, my life was a little easier if you had completed the mechanical technology. But anyway, this is a good efficiency, depending on, of course, the cycle that you are using in terms of production. Right? In terms of ranking cycles, this is excellent. All right. Okay.
Dr. Isaacs, this efficiency is equivalent to the amount of power the plant produces?
This is the efficiency of the plant in producing the power. Remember what I said, that primarily, remember we're dealing with thermal plants here. So it's heat. That's where we are converting heat energy into electricity. Yeah. So whether that heat energy is being used to drive an internal combustion engine, or you're using that heat energy to produce steam. These are all thermal plants. You with me?
Yes, sir.
So the heat energy that is put into the system, which goes through the processing of the steam, the drying of the steam, you work the steam, you get back the wet steam, and you dry it again and use it, right? That's what I mentioned when I spoke about depending on the cycle that you are using, all right? Whether it is Rankine or Carnot or whatever. All right. So the efficiency in terms of your use of the heat energy, because ultimately, what we are taking from the oil or from the bagasse or the fuel wood or nuclear, all of this heat energy is really heat energy that we are using, and we are converting that into electricity. All right. And we are saying that the efficiency in doing that is 37.92%. I don't know if that answers your question.
Yes, sir.
All right, cool. All right. Now, whilst I've given you that piecewise continuous curve, and then we look at the incremental fuel cost versus output. Yes, the operation of our thermal units, we can describe them using either cubic, yes, or quadratic equations. Yes. Now, these equations, as we are saying here, are based on the output of the unit and constant that define the fuel and any operational costs. All right. What do I mean by this? There are some components of the cost that is going to be linked to the output. So there's an aspect of the cost that will be linked to whatever output is being produced. However, when we were looking at unit commitment last time, one of the things we mentioned was the fact that you needed a crew, you needed people. So there were some fixed costs associated with operating a unit. So the equations also look at the variable cost component, the cost that will be dependent on how much you are producing, but there's also a fixed cost. And so the equations are given in this form. Now, I'm showing you here. The highest power here is 2, yeah? But you can have cubic equations. Yes? And so gamma here, let me just change that ink. Gamma, that would represent your fixed cost. This component of the cost function will be output dependent. All right? So that will be output dependent. But this part will be fixed. All right? And we can give the cost, whether in terms of dollars per hour or BTU per hour. That's the last time I'm going to say that, because from here on, we're just going to be focusing on the cost in dollars per hour. All right? So we have alpha times P squared plus beta P plus gamma. and that gives us our cost function. Earlier, we said that the incremental cost would be the differential of this function. So if we have a total system load, PT, yes, then we know that P1 plus 2 up to N would be equal to PT, where 1, 2 up to N would be each unit. All right. So it will be unit 1 up to N as part of the entire system or this plant. Yes. Now the lowest cost in supplying the load as we said before, and I think you have this diagram also. In supplying the load, the lowest cost in supplying the load is determined where the incremental heat rate or incremental fuel cost. So the heat rate is where we would have had it in BTU per hour. All right. The incremental cost is where we have it in terms of the dollars per hour. All right. And so the incremental cost would have been found as the differential of the cost function. Yes. And then that would be plotted against incremental fuel cost, which would now be in dollars per kilowatt hour or dollars per megawatt hour, or the incremental heat rate in BTU per kilowatt hour. Now, what I want you to note carefully is the fact that the incremental fuel cost, yes, when we find that differential, the incremental fuel cost will be increasing as the output increases, which is what I said earlier, that even though I have one line from my buller production, which is cheapest, as I increase the output of that line, the cost to produce an additional unit will cause the overall cost to increase. Yes? So the cost of producing an additional unit will increase. Yes? And it will continue to increase until I then get it equal to the next most efficient, and then we start taking from both. But the key point that I want you to focus on here is that as the output increases, so does the incremental fuel cost. All right, that's the key point from this graph. And so if we go back now to our expression, remember our expression here? We go back to that and we take the differential of this expression. Yes, if we take the differential of this expression, then we get 2 times alpha k, p k plus beta. So it's 2 alpha p plus beta. And of course, note that the unit now changes from dollars per hour to dollars per kilowatt hour. And as I said before, you know, in this space, we're really talking about megawatt hour. So it will be dollars per megawatt hour. All right, so a couple of things that I'm just going to tell you. You just accept them, and then we'll go through an example. All right, I'll go through an example with you, and hopefully it will tie everything that we did last week into this week. It will tie everything together. Okay, so key points. For a thermal plant consisting of N units serving a total load of PT, yes, what we want to do is to determine how we distribute the load. You know, that is something else that I saw persons putting in their labs to suggest that you put on a generator at a particular point to take on the existing load. The generator would be part and parcel of a network. And so the loads would be shared among the generators based on what we're talking about this afternoon. All right? So if you have excess load of 50 megawatts, it's not as if you are going to just throw the generator and it take up that 50 megawatts. All right? They are sharing a load, they are shifting, you know, based on the units that are on the system and a redistribution. Anyway, so I want to determine the distribution among the units. Yes? And we want to do that with minimum operating cost. And if we talk about operating cost, as I have said before, your primary cost of production comes from fuel. Right? And that is one of the things that the utility has been trying desperately to educate us Jamaicans about. Recently, we had a lot of argument about increased costs in electricity bills. What persons did not understand is that just a small increase in your consumption can cause your bills to move significantly because the large component of fuel, which in our case is impacted almost weekly. Every week you get a change in the fuel prices. Right? Whilst that ought not to be so significant to the utilities, given that we are shifting to LNG, which has a more constant price, that's not the case at present because we still have a number of diesel plants and oil plants in our network. And so once the fuel costs change, you're going to see a significant change in your bill. Even if you were to use the same amount, and you will hear persons complain that, boy, them no conserve, them change out all them bulbs from incandescent, and now they're using LED, but the bill is the same. What has changed may very well be the cost of fuel, because the cost of fuel constitutes about 60% of your final bill. All right, so that's why we put here minimum operating cost, and we are highlighting fuel because the fuel is the key component. All right, and if we solve the Lagrangian optimization problem, what we find is that the condition is served for minimum operating cost. Yes, for minimum operating cost for the plant is that the incremental cost for all the units must be equal to some undetermined value, lambda. What are we saying? If we want to operate at the highest level of efficiency, if we want to operate the plant at the highest level of efficiency, then the incremental cost of all the units must be the same. Yeah? Now, this is true when we are taking output from all the units. I say that again. This statement is true when output is being taken. Let me further define that. This is true when additional output is being taken from all units within the plant. All right? Because you may have a situation where there is one unit that is so efficient. Instead of taking output from all three, you'll just be taking output from that sole unit because of its high level of efficiency. All right? And you will not take any output from the other units until the efficiency of this very efficient one becomes as inefficient as the others. I know that may sound a little confusing, but when we get into the math of it, you'll understand and appreciate what we're saying. All right, so this is the condition. All right. This is the objective. This is the objective. Minimum operating cost. That's the objective. To achieve that, that's the condition. All right. So let us see how this plays out. And let's start with a simple plant with 2 units. Let's see how that works out mathematically based on what we are saying here. A plant consisting of 2 units operating under economic load dispatch. All right. For each unit, those are the cost functions. So the cost function for unit 1, A1, P1 squared, etc. BP1 plus C1. Just as we had from our equation before. So we can have quadratic or we can have cubic. So if you in Power World, they give you a cubic model. But if my memory serves me right, and I think it does, for your lab, I do not use the cubic model. I use the quadratic model. Yes. So in that cubic model, it means that you would give the cubic function coefficient 0. That's all. All right. So the program anticipates that you'll be possibly using a cubic. So it gives that model. But we will just use the quadratic. All right. Now, if I want the incremental costs for each of these, then I just differentiate these 2 equations. Yes, and I'm left with lambda 1 and lambda 2. So these are the incremental costs for my units. And note that here I'm using dollars per megawatt hour. Again, students, remember the overarching objective is how do I share the load between these units to ensure that the plant is producing power at the most efficient level. Are you with me? That's the objective. So I want to see, how much load will unit 1 take on? How much load will unit 2 take on? All right. But out there, the demand from the plant will be P or PT. So PT will always be equal to P1 plus P2. All right? Okay. So we can rearrange these equations for my P1 and P2 because, as I said, that's what I'm interested in. I want P1, I want P2. And note, I have now written 2A, A1 and 2A2 as A1 and A2. So it's not that I'm just taking the coefficients here. All right? So I'm calling 2A1, I'm calling that A1, and I'm calling this A2. All right? But as I just said, the total load is what is being demanded from the plant. And that total demand is being supplied by these generating units. So PT would be equal to P1 plus P2, and then I substitute for P1 and P2 in this equation. Now, because this is true, underline it if you need to. Because that is true, it means that lambda 1 is equal to lambda 2 is equal to lambda. All right? So lambda 1 is equal to lambda 2. And to remove any form of bias, to remove any form of bias, then we say that lambda 1 equal lambda 2 equal lambda. So because they are operating on economic dispatch, which means that the plant would be operating at the highest level of efficiency, yes, that is true. So if I substitute lambda for lambda 1 and lambda 2, right, if I make that substitution, then I get PT is equal to lambda minus B1 over A1 plus lambda minus B2 over A2. And then we further simplify. With PT, so we're just taking the lambdas together. We factorize. We factorize. And remember, well, not remember, I don't think I have said it. My objective here is to find an expression for lambda. All right? So our objective is to find an expression for lambda. So I'll bring this over and I get that expression. right. Can therefore find lambda. So that's the expression for lambda. Now, of course, if you look at what we have here, lambda is equal to PT times a number. And then over here, we can call that BT. So it's in this form. So we're just making the comparison. What we have therefore is that AT is equal to the sum of the reciprocals. Yes, the reciprocal of the sum of the reciprocals. Right? And BT is equal to B1 over A1 plus B2 over A2. Note, however, that what we have here is AT. All right. So BT is equal to AT times B1 over A1 plus B2 over A2. All right. All right. So generally, the general expression is therefore that AT is equal to the sum from n to 1. This, of course, is if we have n units on a plant. All right, so for a plant of n units, then AT is given by that expression, and AT and BT are given by these expressions. And then we are going to go into a question. It's 12 minutes after. Yeah, I think we can go through 2 questions here.
Question, sir. Sir, isn't summation AI the same thing as AT?
Go again?
Isn't the summation of AI it's the same thing of AT? Same thing as AT?
You mean? Yeah, you just said the summation of AI. That's what you said, equal AT.
Yes, sir.
Come on, look at the formula. It is sum of 1 over AI, the inverse of that.
I'm asking for BT, sir.
No, 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 no. Look at what we had before. BT, this is AT, yes? However, BT in addition to having AT, this part is AT, but you're multiplying that by this. So BT is AT times B1 over A1 plus B2 over A2. So the general expression is that BT is all of this, which is AT, times this.
Okay, sir.
All right. So let's get to the question. So go ahead, take the question for me. All right. So a couple of things we want to note before we jump into this problem. All right. The first thing is that remember we said last week that once we turn on the unit, it's going to be costing us money. Part of that reason is that once you turn on the unit, there's a certain output that is going to be created. So it would not be there just idling without producing something. All right. Secondly, second thing we want to know is that what we're asked for is the plant's incremental fuel cost. Now, the plant's incremental fuel cost will be driven by the unit that is from which the additional megawatt or is being is being produced. All right. So if both units are producing additional megawatt hours, then both units will determine the plant's incremental fuel. However, if only one unit is producing additional power, then the plant's lambda will be dictated by that unit. All right? And it's obvious from the information we have that the total load is equal to twice the output of each unit. So obviously, we know that by the time we get to 1250 megawatts, both units will be producing the maximum. All right? Okay, so let's take on this question. The first thing we have to do is to determine the cost of production when the units are running at their minimum. So go ahead from here and do that. We have lambda 1, we have lambda 2. So what's lambda 1 equal to? And lambda 2. And this is at minimum output. What are these equal to? All right, so let me help you along on this one. So across there, what's lambda 1? Across there.
Yes, sir.
It is
Lambda 1.
0.0080 times
No, I want the value. I said at the minimum output, what's lambda 1?
8.80 dollars per megawatt hour.
Okay. Come on, Mr. Crosdale, you can help us know. What's lambda 2? Miss Michael, lambda 2. Hmm?
No,
Pardon?
hearing me now?
Yeah, go ahead.
7.36.
Okay. So lambda 2 is 7.36
Megawatts per hour. Dollars per megawatt hour.
Okay, all right. So we have lambda 1 and lambda 2. All right, so because we know we're operating a plant with 2 units, because unit 2 is the more efficient, all right? So it's the more efficient of the 2. It means that we're going to take the additional megawatts from unit 2. But we need to first determine how many additional megawatts we can get from unit 2 before it becomes as inefficient as unit 1. So to determine that, we are going to make lambda 2. So set lambda 2 to $8.80. So $8.80 is equal to 0.0096 P2 plus 6.4. Now what is P2 from this? What's P2, Mr. Sinclair? Mr. Sinclair?
250, sir. 250 megawatts.
250 megawatts.
Yes, sir.
Okay, thank you. Now, the question asked us to determine the, what did it ask us? The question asked us to determine the plant's incremental fuel cost and the allocation of loads when we are supplying 300 megawatts. All right, so, Ms. Michael, back at you.
Yes, sir.
All right. Now, given that P2 will have, what happened?
Nothing, sir.
You sound stressed, Miss Michael. Anyway, come, let's go. Given that P2 would have to produce 250 megawatts before it becomes as inefficient as unit 1. We are supplying 300 megawatts. So how much additional megawatts would we take from unit 2?
50, sir.
Think about it carefully, Miss Michael. What did this represent? What did these represent? What did they represent? The lambda 1 and lambda 2 that we calculated, what did they represent?
Cost, sir, per unit output.
Yeah, but specifically.
Minimum.
Go again?
At minimum output.
Minimum output. So it's lambda at the minimum output. What were the minimum outputs? Ms. Michael, back at you.
The minimum outputs.
From the units.
300.
No. From the units. What was the minimum output?
Oh, 100, sir.
100. So if the minimum output from each unit was 100, how much are we supplying to the system? If the minimum is 100, how much are we supplying?
From both? So 200, sir.
200.
100 plus 100.
Yeah. So we are supplying 200 from the plant. What do we need? So we are already supplying.
Addition.
So the additional would be?
100, sir.
100. So we need an additional 100 megawatts. And we are now saying that P2 would have to be supplying 250 megawatts before we start taking power from unit 1. Additional power from unit 1, because unit 2 is the more efficient. You agree with that?
Yes, sir.
So what's the additional I now need from unit 1? From unit 2? How much would I take? Talk to me, man. We are doing it for the first time. You know?
100 megawatts.
100 megawatts. So what is the breakdown in terms of units? What would P1 be producing? And what would P2 be producing?
P1 will be doing 100 megawatts and P2 will be doing 200 megawatts.
So P1 will be producing 100 megawatts and P2 will produce 200 megawatts. And this would supply our 300 megawatt system load. Remember the criteria. One is that you are going to take from the most efficient unit until its efficiency is as inefficient as the next. Is that clear? So I start with a unit with a $7.36 because it gives me the cheapest operation. Then I test to see how much I can get from it before it becomes as inefficient as the next. In this case, it said I can go up to 250. So I know then I can take the additional 100 megawatts, yes, to satisfy my 300 megawatt load. Is that clear, people? Is there anybody here who don't understand what we just did? Or why we did what we just did?
Yes, sir. I'm a bit lost.
Tell me what you're not understanding.
At the point that you make T2 equal 200 so that you can supply the additional 100, I don't understand. Why the echo? I don't understand that section.
All right. When the two plants, when consider these two units, two truck engines. All right? Because of course, you know, two truck engines. So we're using two internal combustion engines. When I turn on the switch, and the truck them come on. Do you agree that the trucks will be consuming fuel, even though they're not moving?
Yes, sir.
All right. Do you agree that there will be a certain torque on the engines, even though the truck not moving?
I'm assuming so, sir.
Yeah, me assume so. You're an engineering student. There must be some torque on it, even though the handbrake is up. It's producing power. So I'm saying the fact that you turn them on means that you have a minimum amount of power that they are producing. What was the minimum power for each of these units?
The 100 megawatt.
Okay. So if each of them, once they are running, must produce 100 megawatts, how much megawatts would they be producing or supplying to the system?
That's 200.
All right. So how much more do you need to make up the 300?
100, sir.
All right. What we have done here in doing this test is to see what would be the output of unit 2 for it to get to an efficiency of $8.80. Remember this equation? This equation is for unit 2, you know. But this 880 is for unit 1.
I see that, sir, yes.
Cool. So if I need to get all the way up to 250 before it gets as inefficient, then I'm gonna reach 200, man. 200 won't be less than the $8.80.
Yeah.
So that's why I have unit 1 still maintaining its minimum at 100, but unit 2 going up to 200 because the demand on the system is 300 megawatts.
I see it now, sir. I see.
All right. Now, what's the next load that? Oh. Sorry. All right. Now, next, we were asked to determine how we shared the load, but we're also asked for the plant lambda. Yes? Question. Which of the two units is producing additional power? From which unit are we taking the additional power?
From the second one.
From unit 2. All right. So if I'm taking the additional power from unit 2, it means that unit 2 will dictate the plant lambda. Everybody with it? So we're going to find lambda plant, would be equal to lambda 2, which would be A2 times 200. All right, let me not say A2. Make it easier for myself. So that would be equal to 0.0096, yes, times 200 plus 6.4. Yep. And that gives us $8.32. So obviously it is less than the 880, which we expected, yes? So the plant lambda is $8.32 because unit 2 is the unit from which we are taking the additional power. All right. Next. What's the next demand? Next demand is 600 megawatts. All right. So with 600 megawatts, Sashan.
Sir.
At 600 megawatts, would I be taking power from both units, or would I still be able to take the additional power only from unit 2?
From both units, sir.
Why?
Sir, because for unit 2, sir, after it reaches 250 megawatts, sir, it is the same as it has the same efficiency as unit 1, so you can then therefore take the power from both units now. The rest of power from both units.
Excellent. Since I am now sharing between units, yes, we know we'll have to find AT and BT. All right, so we now find AT and BT. So Mr. Allen Chavez.
Sir.
Calculate AT for me. Come folks, we need to get through one that is a little more challenging. So let's just be quick on this. Ms. Donna. Ms. Donna?
Yes, sir.
How do we go about finding AT? How do we find AT?
Sir, would it be
You must have it in your notes.
sir lambda minus BT over PT?
AT is equal to 1 over A1. So you all didn't write the notes?
Yes, sir, I wrote it.
All right, calculate that. You get 0.004363 4363636. All right. And I'm encouraging you to use as many DPs with this, huh? And then, of course, AT or BT rather. BT is equal to AT times B1 over A1, B2 over A2. All right, and that gives you $7.27. All right, some other numbers after that. But of course, since it's a constant, then 3 DPs will be fine because we are dealing with dollars and cents. Okay. Once you have found AT and BT, you know that PT is equal to AT. Sorry. So PT, is equal to 600. So lambda would be equal to AT PT plus BT. All right. So you get lambda would be equal to $9.89. Of course, dollars per megawatt hour.
Sir,
Yes.
I have a question or something I want you to clarify. When you wrote down the formulas for lambda 1 and lambda 2, why we had 2A1? 2A1 P1 plus B1?
As I said at that time, the differential was 2A1. And I actually went back and I circled it and said we are using the 2A1 as A1. I said that. I actually circled both the 2A1 and the 2A2 and said that these were being used as A1, A2. It's just a differential. So it's still going to be a constant. So we could call them K1 or Z1. Doesn't really matter. The point we're making is that the coefficient of P is A1. So the 2 just came about because we differentiated the P squared, right? But we went and circled the 2A1 and said that that was equal to A1. All right, so lambda is equal to $9.89. Now, the theory we have already established is that for the plant to be operating on economic dispatch, that both units must be operating with the same lambda. So I now substitute lambda into P1 and P2 for P1 and P2. All right, so for economic dispatch, lambda is equal to A1 P1 plus B1, which of course is now equal to $9.89. So you rearrange, you get P1 here to be equal to 236.25 megawatts. And again, lambda, because remember, this is economic dispatch, and economic dispatch says that the units must be operating with the same lambda. Okay? So lambda is also equal to A2 P2 plus B2, and that is $9.89. You rearrange, and you'll get P2 to be equal to 363.54 megawatts. When you add these two, it comes up to 599.79. All right. I can tell you that that is because I rounded off lambda. 80. All right? So that occurred because of this. That's why I'm saying, especially in exam setting, what you may want to do is just to keep the value that you get in the calculator for AT, and then use that to find your BT. All right? So for this one, when we are supplying 600 megawatts, whoops, sorry about that. PT is 236, P2 rather, P1, oh boy, and P2 is 363. We add them, we get back our 600 megawatts. And of course, the plant lambda will be dictated by both units. All right? And so we can, so this is how it is shared, and then lambda is equal to $9.89. All right? And then finally, we are told that we want to find the breakdown when it is at 1250.
You could go back 2 slides for a quick second.
We could finish this up first.
All right, sir.
For PT equal 1250, yes? What's the maximum output of each unit? Go back to the question, what's the maximum
25.
output of it? Huh?
625.
625. So obviously, both units must be supplying their maximum. Everybody agree?
Yes.
Yeah, so we don't have to go into anything fancy in finding, a lambda for each and then, share. We know, based on what we have before us, that it is both are operating at their maximum. So P1 is equal to 625. Yes. 625 megawatts. And P2 would be 625 megawatts. The big question, however, is what's the plant lambda? Huh? What's the plant lambda? How do we determine the plant lambda? How do we determine lambda? Period. What is lambda?
So we determine the plant lambda from both units.
No, but what is lambda? Let's start there. What does lambda represent? What's the definition? What we call it? What's lambda? What's there? What's lambda?
Incremental.
I think it's the Lagrangian multiplier.
It's incremental fuel cost. Right, Mr. Dwyer?
Yes, sir.
Yeah. What that mean?
Sir, which unit we're getting the additional power from?
So the unit from which the additional power is being taken. Thank you, Ms. Downer. So if that is the case, which one of these units reached their peak first? Which one reached 625 first? Come on, man, look at the question. Look at what we have been doing. Which one of the units will reach maximum first?
P2.
Unit 2. Right?
Yes, sir.
So that one would have reached its maximum because we saw that initially when we were supplying 300, unit 1 was at 100 while unit 2 at 200. When we went up to 600, unit 1 was at 200 and had unit 2 360. All right? So obviously unit 2 will reach its maximum first. So which unit was the additional megawatt being taken from?
P2.
No. Think carefully. If it reached its maximum before unit
P1.
1, it must be unit 1. Because unit 2 is already at its maximum, while there was capacity on unit 1. You with me? So when 2 is pushing out 625, 1 was at 500 and that, then it come up to the 600, then it come to 625. As the load was increasing towards 1250. So it means that the additional megawatt was coming from unit 1. So the lambda plant will be dictated by lambda 1 at P1 equals 625. Which is why I said at the beginning, students, that this particular topic is not one you're going through some formula. You have to think about it. This is engineering. This is not just getting two formula, plugging in two numbers. You know, we can ask any sixth former to do that. You know what? The cost of going out there into the working world to make decisions. So you have to start make some critical decisions right here in power systems. All right. Now I know we are pretty close to the end. So I want 1650. So let us take the next question. And yeah, let's see how we can navigate through this one. So take this one quickly. While you do that, I will take the register. Alrighty then. Adams.
Present, sir.
Chavez, Allen.
Yes, sir.
Barrett. Okay. Let's do this again. So I had Adam, Chavez, Barrett. Blake, Rajay, and Devon.
Yes, sir.
Here, sir.
Bruce.
Here,
Buckley.
sir.
Buckley, Burns.
Yes, sir. Burns is here, sir.
Campbell.
Here, sir.
So Burns.
Yes,
Are you,
sir.
are you in another class?
No, sir.
Okay. All right, Copley. Copley.
Here, sir.
Crasdale.
Here, sir.
Daly.
Here, sir.
Dale.
Present here, sir.
Daly.
Daily, here, sir.
Down at the places.
Here, sir.
Dwyer. Ellis.
Here, sir.
Ferguson.
Here, sir.
Finley. Finley. Francis.
Yes, sir. Yes, sir.
Gibson.
Here, sir.
Henry.
Here, sir.
Hewitt.
Yes, sir.
Jeffrey.
Here, sir.
Johnson.
Yes, sir.
Kamika.
Yes, sir.
Carr. Carr. Leon.
Yes, sir.
Mason.
Here, sir.
Merchant. This man in the class, right? Montague.
Here, sir.
Norton. Phillips.
Here, sir.
Porter. Ramsey.
Here, sir.
Ready.
So here.
Reed, Christoph, and Dario.
Present, sir.
And that's Dario, right?
Yeah, Dario, present.
Okay. Rose.
Yes, sir.
Kamala Russell.
Here, sir.
Shand.
Here, sir.
Shirley. Sinclair.
Here, sir.
Michael.
Present, sir.
Smith.
Present, sir.
Thomas.
Here, sir.
Venna.
Present, sir.
Watson. Williams. And Zheng. Alright. So Michael not there today. Alright. It is now 3 minutes to the hour. I don't know why we're going to do this, but we're going to do this problem in 3 minutes. As before, you'll find the differential. So whilst we gave you the lambda expressions, here we give you the cost functions. All right? And what you want to determine is one, the incremental fuel cost of the plant and the total cost of production. So what we have here are the cost functions. So once you have determined P1, P2, and P3, yes, you're going to substitute it into the cost functions in order to find the total cost. Is that clear? Is there anybody who don't understand that?
Yeah, go on again, sir, please.
These are the cost functions, dollar per hour. So what you need to find is P. Once you have found P1, P2, and P3, you're substituting this in order to get the cost. We're trying to find the cost of producing of supplying 800 megawatts. These are the cost functions. So when you find the P's, make the substitution and you get the cost value.
Sir, can you resume the recording, please?
Thank you. Secondly, what we want, in order to find P1, P2, and P3, the first thing we need to do is to determine lambda 1, lambda 2, and lambda 3. So you have lambda 1, lambda 2, lambda 3, whatever these are. I'm not giving you a value. I'm just saying you need to find them. As a matter of fact, you know what? Just find lambda 1, 2, and 3 for me, please. All right, so what's lambda 1?
17.4 dollars per megawatt hour.
17.4. Lambda 2?
$19.2 per megawatt hour.
Lambda 3?
$6.1 per megawatt hour.
Okay. All right, so assuming that these values are all correct. Next, because unit 3 is operating at the highest level of efficiency, what you're going to do is to make an initial test with unit 1, which is the most efficient. All right, so you're going to now say 17.4 is equal to A3 P3 plus B3. All right, rearrange. What is P3? What is P3?
104.44 megawatt.
104.4 megawatts. So you are now going to look back at the operation of the units. All right? And based on what P3 is showing, yes, its maximum is 300. So we would not have reached that maximum. Are you with me? Because when we get this 104 kind of looks small, though. So we're moving from 17. Oh well, is what that? $1.30? Anybody else got the 104? Because the minimum for P3 for unit 3 is 90. And as the most efficient unit based on what we have here, for it to just add 10 more megawatts or 14 more megawatts, it look kind of small. Anyway, anybody else got 104? Did anybody else get 104?
Sir, I'm not sure if my answer is correct, sir. But
I didn't ask that. Just tell me what you get.
I get 117.5, sir.
Okay, that sounds a little better. The 104, it sounds a little close to me. All right, that sounds a little better. But anyway, the point still remains. Because unit 3's maximum is 300, yes? It means that when you get to 117, you would also be taking power from unit 1. Are you with me? So the first thing you're going to do, since you now know that you'll be taking power from multiple units, you're going to find AT and BT. AT is 1 over A1, 1 over A2, 1 over A3. Reciprocal of that. BT is AT into B1 over A1, B2 over A2, B3 over A3. Calculate these, right? Listen, you're going to work, you're going to do it again, you know. So I just want the quick values here.
Sir, ATS 0.036569920.
All right. And BT? I'm just taking your word for it. 0.035.
Hold on a second, put it in a
So
calculator.
forth.
7.59632.
7 point?
59632.
Yes, sir, we get 7.5963.
All right. As I said before, because you're dealing with dollars and cents, you really only need 3 DPs. All right. Because you're going to come down to 2. Because the answer you give must be a dollar in terms of dollars. So it will be, cents is 2 decimal places. Anyway, so we have AT and BT. You're now going to find lambda, which is equal to AT PT plus BT. All right. Once you have found lambda, you are going to substitute lambda being equal to lambda 1. So you use the equation for lambda 1, the equation for lambda 2, and the equation for lambda 3, and you find P113. So once you have found lambda, lambda 1 would be equal to lambda 2 would be equal to lambda 3, which would be equal to lambda. And from that, so from these, we find P1 P2 and P3. Okay? All right. Well, this won't be form part of your assessment on Saturday. And you'll have other work to do. So I'm not going to ask for a submission, no. But listen carefully. Just make sure you have it completed when we come to class next week. I repeat, I'm not asking for a submission. Make sure you have it prepared and completed when we come to class next week. Just a reminder about this weekend. It would be, you would need to write as if you're doing a regular examination, then upload. Yes. I have seen persons, at least 2 persons recently, submitting work to me and gave me this bunch of JPEG. All right? Let me warn you folks. If you do that for your exam, I am looking at the first page. As far as I am concerned, that is what you would have submitted. I am not, and I repeat, I will not be going through your individual pictures. You upload your document as a PDF. I know I'm speaking to, I'm preaching to the choir because most persons have been doing that. But I still saw persons submitting their work quite recently as individual JPEGs. All right? I wrote them, warned them about it, but I do not wish for that to negatively impact you on Saturday. The exam begins at 7 p.m. It ends at 7. You know, I need to double check that. Anyway, it begins at 7 and ends at 9. All right. Let me make sure of that. I don't want to mislead anyone. So let me go there. Yes, it begins at 7 and ends at 9. All right. As usual, you will have 15 minutes to upload your documents. Yes. And of course, the link will be there for uploading. The link goes dark at 9:15. Students, if you are not comfortable with the uploading, I encourage you. I think we had given you a test link some time ago. That link, I believe, still exists. So I encourage you to practice how to upload if you're not sure how to do that. Yes, I will not even read the excuses. If you don't know how to do it, practice, ask a friend how to do it, because I don't want any excuses come Saturday. I will mark at 9:15, I will mark all the documents that have been submitted to me. If you send it via email, I'm gonna delete it. If you send it to me attached to a message in a Schoology, I am going to delete it. So please do not waste your time. Spend the time now. Look at make sure your computer working. Go through all of those things. Yes, I have chosen a time that the traffic on Schoology is very low. All right, that's the reason I've chosen that period.
Not to break it still in, sir, but in where I live in, sir, we have a really bad situation with internet.
So I am gonna ask you to shift and find and make the necessary arrangements. Make the necessary arrangements. We said this from day one. I fully understand what is happening with respect to internet connectivity, right? But you need to make the arrangements.
All right, sir.
Don't sit in the ants nest and then tell me that, sir, I was sitting in an ants nest. All right?
Okay, sir.
I have made these dates known to you for the past 7 weeks. Make the necessary arrangements. This is one time you may need to just, spend the $250 and say, why, this is for the exam. All right? We're decision makers as engineers. We solve problems, not tell why we fail. Okay? All right. Yeah, that's it from me today.
Sir, it states up to project management, sir. Dr. Isaac.
Yes, sir.
Yeah, I'm asking if it takes it straight up to project management already last week.
Sir, the test is based on the module outline that I gave you. So you look at your module outline. I tell you all these things from September. So forgive me if I'm not going to repeat myself today.
Excuse me, Dr. Isaac.
Yeah, man, I'm listening.
Sir, could I ask something based about the previous question that we were doing? Just for clarification.
Sure, go ahead. Man.
Sir, when we differentiated the cost function to get lambda, we would use A instead of 2A, right?
I don't believe this, Differentiate the function and the coefficient you get, that's it. That's the coefficient.
Okay, sir.
So the first one will be 0.14. The next one will be 1.1. The other one will be 0.9. Just differentiate the function.
Sir, because you were saying something earlier about using.
I said it based on the question that was asked. I simply repeated what I had said earlier in the lesson.
Okay, sir. Thank you.
Yes, I was just repeating that. Oh, it's just a matter of differentiating the function. All right. Yeah. That's it. That's it. That's it. All right. Have a good one. All the best for Saturday.
All right, thank you, sir.
All right. Cheers.